So let me tell you a little bit about self-driving, which is probably the most exciting part for you. Who cares about my life? So if you want to do self-driving, there is like 3 things that you need to think about, and you probably haven't thought of these 3 pieces. The first one is this thing on the left, which is you need to be able to build self-driving vehicles at scale. And that's actually quite hard. It's something that there is a lot still to be done in order for this to happen. And one of the things to think about is that self-driving vehicles are not standard vehicles. And it's not just about these weird sensors that they have on the top. It's also about the fact that they have to have redundant steering, redundant compute, etc., because there is not going to be a human right to take over if there is any problem in the future. At the same time, the other piece that you need is the software, is the brain of the self-driving car, right? It's able to drive safely in the environment. This is what I do for a living, and to me, this is the most exciting part, but it's just one of the 3 pieces that is necessary. The third piece is the network. What does that mean? Is that, as you probably have observed, with self-driving vehicles, the model is going to change from car ownership, which is what we see today, to basically fleets that are shared, to just having a service, right? Such that you can call your self-driving vehicle, it's going to pick you up, but that self-driving vehicle is going to serve many, many other people, not just yourself. And this is great because we need to share resources with the rest of the world. At Uber, it's something that the company excels at doing, so this is one of the big advantages to be here. All right, so in terms of the hardware, this is my only slide of hardware today, okay? What are these self-driving vehicles? They are amazing robots. So there are things like, this is our latest, greatest prototype that we actually is now a couple of weeks old. And what you see here is, so we have a whole bunch of sensors. We have many high-definition cameras around the vehicle that sees 360 degrees. We have the LiDAR spinning on the top that give us 3D information. We have GPS, radar, IMU. We have a whole bunch of ultrasonics, etc. So it's an over-complete set of sensors. And we have also a customized compute with a lot of compute power, but there is a lot that you need to do in order to be able to drive. So even though it's a fantastic computer, I wish it was a much bigger computer. All right, so what does the self-driving vehicle see? I'm showcasing here 2 of the sensors. This is just driving around, in this case, the US. On the left-hand side, you see one of the cameras. On the right-hand side, you see what comes out of the LiDAR. So this for the LiDAR is view from the top, okay, and it's 3-dimensional point clouds of rays that basically hit the environment, okay? So the left-hand side is great for semantics, right? We can sort of understand what are the different things, and the right-hand side is very good for distance, for 3D. Where are things in the world, independent of what they are? So to notice that these sensors are actually very complementary, and this is one of the reasons where we have this over-complete set of sensors, because this is a very hard task, right? You don't want to limit yourself. You want to make sure that you arrive to a solution, and then you can look at, is this the minimal set that I should bring to a scale? So how does self-driving work? So for most of the real competitors for self-driving, this is sort of the software stack of how it works. The first thing that you have is the sensors, right? Again, in this case here, I'm showcasing what the vehicle sees from bird's eye view, so from the top. Imagine you're at infinity and just looking down. So the first thing that we all do is we localize where the vehicle is in the world with precision of a few centimeters. Why do we do this? Is because we have these fantastic maps of the environment that basically tells you, in the absence of dynamic objects, where do you expect things to be? Where do you expect the lanes to be? Where do you expect the different rules at different, for example, intersections to be? Where are the crosswalks? Where are the traffic lights, etc.? Okay? These maps, you can think of them as a sensor. You shouldn't fully believe them, right? Because the world might change as you drive, right? Maybe the map that you created a month ago is slightly different today because, if you live in Toronto, there is construction every 2 seconds. Okay, so now we have basically localized the vehicle. Ooh, nice. Interesting. Okay, whatever that was. So the next thing that we need to do is we need to localize the dynamic objects and the static objects that weren't part of the map. In this case, what you see here is the vehicles, and the pedestrians are basically these small circles, and there is some bicycles as well. And basically, in 3-dimensional space, you need to say where everybody is. And it's not just about understanding the present. We basically understand the past as well as the present because we understand how things move in the environment. Now, if you think of how you drive, the past and the present is still not sufficient. You need to sort of reason about what are all these actors going to do in the next few seconds. So this is what I'm showcasing here with these trajectories, right? We want to hallucinate for each of these actors, what are the expected set of possibilities, and what's the probability of those things happening, okay? And this is important such that, for example, if this vehicle or this pedestrian is gonna jaywalk in front of me, probably wanna, reduce my speed to make sure that I have enough safety buffer. Now, once I know what the past, the present, and the future is going to be, I can have a focus of interest on a region around myself, and then basically I use this for planning. I decide what is the safest trajectory to execute, and then I execute this trajectory. Now, between my vehicle model and the real world, because of friction, because of many things, there is a deviation. And then basically control, what it does is that given what the vehicle really executes in practice, it tries to bring down the vehicle to the path you intended to do in the first place. And this runs in a few milliseconds as well, okay? So this is sort of the whole process of self-driving. So it's very, very complicated, right? It goes from, perception, prediction, motion planning, control. And this is autonomy. This is only a piece of what you need to do for self-driving. Okay, so in the remaining of the talk, I'm going to show you some videos. Okay, so sit down, relax, and watch with popcorn. This is basically the kind of things that we sort of do in the lab. We were computer vision experts when we joined the Uber lab. So one of the first things that we did was to bring the computer vision algorithms to be beyond the state of the art. What you see here is in a few milliseconds, you can run an object detector that works for different classes, different times of the day, different weather conditions, and you see that the cameras can be tricky, they can be fog, they can, at night you don't see much. It turns out that neural networks, so AI, can do much more than humans in this sense. You can see at night, while you don't necessarily see within these frames. Now, yes, driving with detection, which is placing these bounding boxes, is actually dangerous. Why is this? Because the detector might not place a bounding box where there's actually an object, and if you don't reason about it, right, you're going to crash into it, right? So what is important is that you explain every single piece of evidence. In the context of images, explaining every piece of evidence is the problem of panoptic segmentation, which basically says that for every pixel, I want to say what the class is, whether it's road, vehicle, etc. At the same time, for countable objects, I want to delineate where they are in the sensor, okay, where they are in the image space. Right, this car is different than this car over here. Now, in terms of self-driving, just reasoning about images is really not relevant. What you need to do, or not so relevant, what you need to do is reason in three-dimensional space, right? Because you need to plan your maneuver in this 3D space. So we build in the lab many generations of algorithms that are able to fuse information from different sensors within a single neural network and reason in a few milliseconds about, again, all the actors of the different classes of interest. On the left-hand side, you see things projected into the image. On the right-hand side, you hopefully see things in bird's eye view where these different actors are. What I'm showing you here is independent processing per frame, just to showcase how accurate and how stable the detectors are without having temporal consistency. Now, the same thing of what I said, that we need to reason about every piece of evidence in image space, we need to do in lidar space as well. So this is just showcasing that you can color code, right, for every point, the semantic category of interest, whether it's a pedestrian, a bicyclist, whether it's part of the road, whether it's an other thing that is in the middle of the street, or it's part of the background. Now, as we build self-driving, what is important is that, as I mentioned before, there is all these different pieces, and this seems like a very daunting task, right? And typically, you have hundreds of engineers working in all these things. So what separates Uber from everybody else is that we build holistic models that, with a push of a button, you can train the system, and at the same time, targets many of these tasks while being explainable, okay? I can talk about it for hours and hours and hours, but believe me, I'm going to show you just some examples so that you see how we build the technology encompassing more and more of the software stack. So the first thing that we did was to take all the detection models and all the prediction models and have a single neural net that shares computation and outputs everything together. And this runs, again, in a few milliseconds, and it's much more accurate than what you see if you do traditional techniques that are in other software stacks. So what I want you to see here is these are, in this case, I'm going to showcase vehicles. Different colors means that it's the same object tracked over time, right? So if I think that this car is the same car in the next frame, it's going to have the same color. And bear with me, there is a lot of colors because there is a lot of vehicles that you see in these snippets. These dotted lines are basically our predictions into the future. So we detect where they are, we track how they move over time, and we predict how they're going to be moving in the next few seconds, okay? All within a single neural network to do all these tasks. So we went from this one step ahead, and I want you to focus on the bottom right video. And what you see here is that we are going to not only detect, predict into the future, but also we're going to sort of reason about the intent. And this is important in order to do the proper motion planning. So intent is going to be depicted with different colors. The more yellow it is, the higher the probability that yes, continue driving. The more red it is, the higher the probability that it's going to get to a stop. And the more purple it is, the higher the probability that it's park. And it's important to make the distinction between park and stop, because probably what you do as a self-driving vehicle is going to change depending on the semantics. And if you think about it, it's actually quite hard, the nuisances into what's the difference between park and stop. In this case, you see a whole bunch of car parks. And with arrows, what you see here is also probability of continuing the same lane as well as turning or basically changing lanes. Now, what is interesting is that as humans, we actually, if we are good drivers, and we tell the rest of the people that are driving, right, the rest of the actors, what our intention is in the first place, right? And the self-driving vehicle should be able to use this information in order to drive more safely. These are turn signals, hazard lights, etc. Right? So in this case, what we have is, again, everything is neural nets, like what we do in the lab, right? So another neural net that is going to reason in space-time, and basically it's going to say, giving a detection, whether there is any turn signal that is on. Sorry. I think I talked too fast and too much. So in this case, if it says I don't know, it's because there is occlusion. If it says it's the right one, it means it's the right turn signal within the vehicle, so you need to flip it if it's this way, right? And if it's the left one, it says it's the left one. If it's both, right, you have the hazard lights. What is interesting is that we train the network with just a few examples, and the examples are basically just saying where is the right turn signal on, or the left, or whatever, but we don't say where it is the turn signal. And then the network basically learns to pay attention to areas that look like turn signals without us telling the network that that's actually the place. This is the way to get training data very, very cheaply, and this you can scale very fast. So in this, going more and more into this autonomy, basically you can now do the full autonomy within a single neural network. And bear with me, this is a very complex video. So hope, let me explain it to you. We're going to see maps. And in this case, we're going to predict where the things are. So these are detections. Where they're going to go into the future, these are these trajectories. And I'm going to showcase also the cost volume for motion planning that is output by the same neural network, so single neural network. This means what I'm showing here is the areas of low cost. Where should the self-driving vehicle go in the next few seconds? And it's projected into the ground. And I'm projecting time. It's a three-dimensional cost volume projected into 2D. Okay, so it's a bit complicated to see, but different colors imply different points in time into the future. Okay, this is just to give you an understanding of what the network is thinking in terms of where the self-driving car should go. So one thing to notice is that it learns multimodal distributions. In this case, I can take a right, I can continue straight. In the previous case, I can change lanes. And it learns this just by imitating what human drivers do. Okay, so with very, very sparse signal, you can actually learn to do the whole software stack. This is actually a breakthrough in self-driving because typically it really takes hundreds and hundreds of engineers for years to arrive to something of this level of accuracy. And this is a single neural net, a bit of training data with very well-designed architecture can actually do this. And the architecture is complicated. This is a deep structure model for those of you that work in AI here. Cool. So I mentioned before, so this is about autonomy, right? There is other aspects that you need to reason about. So you need to build maps of the environment, and these maps have two types of components. For localization, to know where you are, you need to reason in 3D, and these are one of our greatest techniques to actually build using LiDAR and images, three-dimensional maps of the environment. Okay, and so as you can see, we have removed all the possible moving objects because they will not be there in the next few seconds. The other type of map that you need to reason about is semantics. And these semantics are things like lanes, whether you can pass or not, where are the crosswalks, where are the different things that you can do, whether you're allowed to pass and red light, etc. And so we have built different instantiations of technology for this. What I'm showcasing here is just one of the latest algorithms. And the idea is that in this case, I'm showing half a kilometer of highway, single pass of the vehicle, and automatically you can actually predict very complex topologies of these lanes. In this case, I'm focusing on things like merges and forks, which are actually quite hard to estimate. Now, this is fully automatic. It has been estimated by a third party that building maps just of the US once will take $1 billion. $1 billion. With this, you can have orders of magnitude cheaper maps with the same level of accuracy, right? So this is a big deal to be able to build automation for these maps. But it's not just about creating the maps offline, as what I was showing you before. It's also about reasoning online, because the maps can change. In this case, I'm showing you driving in highways. And in this, what you're seeing here is tech that online, single frame at a time, can estimate all the lanes with very, very high precision, and all the lanes in 3D. We use this technology to drive the fleet for hundreds of miles without intervention automatically, without requiring a single map. And this is something that you don't see out there. My obsession for a while is being construction. These are construction sites on my commute from home to work. I have 25 minutes commute and in Toronto, and these things appear, every day there is a different one. So I have a very nice repertoire of pictures. So as I said, I was obsessed with this. One thing to notice is that they can be quite difficult to understand. Like, this thing is a cone, but it's not really a construction. This guy looks like a construction worker, but he's not. This guy here in Toronto is crazy. This is actually a new tram stop. It turns out that the rules of traffic change with the trams, and in this case, the self-driving vehicle has to understand that this thing is a new stop, right? It's really, really hard semantically. Okay, so we build technology to handle construction online. So this actually runs on the vehicles, on the fleet out there, on our fleet. And what you can see here is, again, neural nets that are able to reason and have memory such that you can map the full construction site. And this is important because where you can drive, probably in a lot of construction sites, depends on the first frame of when the construction started. This just shows, the very high level of accuracy that we can have in 3D space as well as semantics as we go. Other things that are important for self-driving are simulation. You need to test that your self-driving vehicle is safe, and you need to be able to train on things like near accidents, etc. You don't want that to happen, right? You don't want to wait to see an accident to be able to handle an accident, for example, right? So we build these assets and the three-dimensional worlds automatically by just driving around the world. And then we can simulate scenes and how the sensors will see. These are different vehicles, pedestrians, cyclists, etc. We have AI systems that are able to simulate crowds of how vehicles drive in the environment. And then we can also simulate the sensors as well. So this is a big generative model of the world. In this case, on the left-hand side is the real LiDAR. On the right-hand side is the simulated LiDAR. It's almost the same. And it turns out that you can test and train the systems with either real or simulated. It doesn't really matter, which is great. And here you see the simulated scenes, simulated LiDAR, which is, it sees only a subset of things, and our perception algorithms just on it. So the last thing I want to show you is that we need to simulate not just LiDAR, we also need to simulate images and other sensors. And I will ask you a question. One of these vehicles is fake. Which one is it? Any ideas? Who thinks it's the big vehicle that is getting into our lane? Who thinks it's the one in front of us? What about the pickup truck? Come on, guys. This is worse than my, machine learning classes like that. All right, so it turns out that this is the one on the left, okay? So this guy here is fake. He wasn't there in the first place, right? So you can actually really fool humans. You can fool neural networks, right? So you can compose exponentially many examples by actually doing this technique where you take the real world and you extract, you put more information and you remove vehicles as well, okay? Okay, so I show you, some of the things that are important to work on in order to get to self-driving, and there is many, many benefits. You can lower the risk of accidents. There is 1.3 million people that die every year. You can provide mobility for the elderly and people with disabilities. As medicine gets better, there is more and more sectors of the population that actually belong to this category, so this is very important. We can reduce the cost of transportation. If you look at vehicles, 95% of the time they are parked, right? There is so much more that we could do with that space. We could actually have parks and, have your kids when you have them, play there. Now, innovation is not sufficient, right? We can build this technology, and if each one of you goes and buys a self-driving car, the world is going to collapse with traffic, right? So instead, it's really the combination of public transit, car sharing, and ride sharing where the solution to this lies. And I want to share with you, it's not just about self-driving vehicles. There is much more that goes beyond this in the near future. You take your self-driving vehicle, you arrive to this nice building, you go to the skyport, and you have these nice vehicles waiting for you. This might sound science fiction for you, but actually, this is not, so far away from reality. And we have a big program called Uber Air or Uber Elevate on this topic. And the world is three-dimensional, right? We should use it. And all this stuff, is much closer than you think. Thank you.